Hello everyone, and once again welcome to the fundamentals of particle and fluid solid processing lectures. We were discussing about the transport of fluid solid system and specifically the slurry transport. We have introduced this topic and we have seen that what happens, how to calculate this average density or say the mixture density of the slurry. Now coming to the viscosity of this mixture, we have seen Einstein equation specifically for the solids concentration when it is very low, or say the volume concentration of the solid particles is lesser than 2%. Then also the slurry consists of uniform spherical particles, then this expression is valid. But for non-spherical particles and of higher concentrations, there is significant deviations from the predictions that it provides. Now for the concentrated slurry, which mostly behaves as a non-Newtonian liquid, there are several rheological models available, like the power law, Bingham plastic and Herschel-Balke models. Now there are also slurries, but rarely in practice, which basically exhibit time dependent flow behavior like the thixotropic or the rheopectic material. We will not go into these details of these things because I assume that this terminology and these models you know. We will have an overview of the power law, the Bingham plastic, and related to these models, how we calculate or how we predict pressure drop for the slurries that exhibits this power law and the Bingham plastic behavior. So we will mainly focus on these two categories. So for the power law, we know its constitutivity equation is something like this, which is also popularly known as Oswald-de equation, where this K is the consistency index and N is the flow behavior index. So the shear stress and the strain rate is related by consistency index and the flow behavior index. And since in this case the viscosity is not a constant, because the viscosity varies with the shear rate. So that means there is this absolute viscosity or viscosity, so this terminology becomes insufficient or it is meaningless. So that is why in non-Newtonian fluids we call that as apparent viscosity. At a certain shear rate, this provides, this expression provides this mu apparent, which is the apparent viscosity, which we can have from this relation. Now we can see from this schematic how this relation varies. So this flow behavior index, when it is 1, then this expression basically the K becomes the mu, which is for the Newtonian fluid or the Newtonian liquid, for n is equals to 1. For n greater than 1, these fluids shows the shear thickening behavior, or we say the dilatant fluid or the liquids. And in other case, when n is less than 1, we say these are the pseudoplastic material or the pseudoplastic liquid, or the shear thinning, because with shear rate we can see in the dilatant case the shear stress increases and the viscosity will increase. In the shear thinning cases, we see that as we increase the shear rate, the viscosity goes down. So these are the basic things we have seen in the fluid mechanics or the fluid dynamics classes. Now what it leads to, this shear thinning or the shear thickening behavior, with changing the value of n. So Say the velocity profile of a Newtonian fluid in a pipe or a liquid in a pipe, it would typically give us a parabolic profile, which is represented by this line. Now, in case of pseudoplastic fluid, that is n less than 1, it shows a blunt profile. Okay. As we decrease the value of n, the profile becomes more flatter and flatter, or the flow profile becomes more plug like scenario, plug flow like behavior. But in case of dilatant fluid, as we increase the value of n, because this is for n is equals to 1, that is the Newtonian fluid parabolic profile, as we increase the value of n, we see this becomes more and more sharp at the front end. For very high value of n, that is greater than 1, much greater than 1, this velocity is seen to be linearly varying in the directions, that we can see here, that it is almost a linear variations till its center. So, this becomes the flow behavior or the flow pattern of the slurry according to its rheological characteristics. So, if it behaves as a shear thinning liquid, it falls in this category. If it is a shear thickening fluid, it goes in this category. So, most slurries exhibits shear thinning behavior, because the hypothesis is that this slurries contains the fine particles which creates aggregate with the increasing shear, and these aggregates basically have a lower resistance to the flow. So, it becomes more flat like profile in this case. The gradient is lesser in the middle. Now, the most important factor in the slurry transport is to predict or calculate the pressure drop that is required, because this in other way dictates the mechanical energy that is required or the pumping cost that is required. So, now if we do the momentum balance like we have done in fluid dynamics for a Newtonian fluid, in order to have a velocity profile, we see that for laminar fully developed flow in a horizontal pipe of diameter d, we can have this as a value of the average velocity of the slurry that exhibits power law behavior. So, this profile basically depends on the value of K, which is the consistency index, as well as the flow behavior index along with the diameter of the pipe. So, the pressure drop, this if it is rearranged, the pressure drop per unit length can be expressed in terms of this average velocity and K as well as and the N values. So, this gives us the pressure drop estimation laminar condition in a horizontal pipe for power law slurries. Now, interestingly, if we look at this expression, we see that for n is equals to 1, we have seen that K becomes mu, and in that case this expression reduced to the Hagen-Poiseuille equation, which should be in this case, because if it is 1, it becomes a Newtonian fluid, and we know for the laminar fully developed flow of a Newtonian liquid in a horizontal pipe, the pressure drop is related by this famous expression. The other way to estimate the pressure drop is by friction factor method. Now, the friction factor in a horizontal pipe, we have also seen this expression in fluid dynamics, where HF is the head loss, the frictional head loss. This is the fanning friction factor. The other parameters are well known to us. Now also from modified Bernoulli's equation, in case of this horizontal flow, we know the frictional head loss and the pressure drop, how it is related. This head loss is basically having the unit of length. Rho m is the mixture density. So which means from these two expressions we have del P and the fanning friction factor relation, which is also well known to us. Now for vertical flow with varying cross sectional area, including head losses due to say positive head or negative head that comes from pump, valve, fittings in a pipeline network, we can apply Bernoulli's equation in a modified form, which would look like this expression, where summation of H is the sum of all head owing to these pumps, turbines, say valves, fittings, bends, all these kind of scenarios. The del Z is the vertical height difference between exit, say this exit we designate as 2 and the entrance is 1. So, Z2 minus Z1. So, this can be the generic expression for a pipeline network depending on the orientation, be it a vertical flow or they say the horizontal flow. Now, the thing becomes important in friction factor related pressure drop calculation is the regime calculation or the flow regime, because is it in laminar or in turbulent. Depending on that we can consult the friction factor chart or we can consult the appropriate correlations to find out what is the friction factor value. Now this regime we identify with the help of Reynolds number in Newtonian fluid. Similar to that, here also we apply the concept of Reynolds number definition, but in a modified form. Here the modification is done through the effective viscosity, because this is we are talking about non-Newtonian fluids or non-Newtonian liquids. So there is no absolute viscosity, we have effective viscosity. So this how this effective viscosity is now defined. If we, because we have seen the definition of rho m, which is the mixture density, V average we know, we have seen the expression previously for the power law fluid. So if we know now this effective viscosity expression, then we can calculate Reynolds number for that particular power law exhibiting slurry, and we can understand whether that is in the laminar or the turbulent regime. So one part is that to calculate Reynolds number of the existing slurry that exhibits power law behavior. The other part is that what is the transition Reynolds number in such slurry, because for the Newtonian case we know that margin is to be 2000 or to the 2100. Below this it is laminar, and higher than that transitional, and then we have the turbulent regime. So here what is that critical Reynolds number or the transition Reynolds number? So we have twofold issues here. So let's try to see one by one. So now from Hagen-Poiseuille equation we can write this in a slightly oriented form, reoriented form. So this is the expression of the Hagen-Poiseuille. We have just rearranged that in order to write this term as tau 0, which is shear stress at the wall. So for Newtonian liquid we can write the mu in this form by rearranging the Hagen-Poiseuille equation. Now similarly in power law liquid also we can write this effective viscosity as this expression. Now also we have seen what is the del P by L previously. So if we now try to write this tau 0 in terms of del P and substituting this del P in this expression, we find an expression something like this, where we can see the shear stress at the wall is basically dependent on the consistency index, flow behavior index, average velocity and the diameter of the pipe. So now that means this effective viscosity, which is tau 0 divided by this parameter, if we now substitute this expression here to find the effective viscosity, we see we can derive this expression for effective viscosity. So which means the effective viscosity is a function of the consistency index as well as the power law index or the flow behavior index. Now the Reynolds number, consequently, because we started with this expression, we wanted to find what is effective viscosity, what is the expression of that. Now we have now got that expression, so we substitute that effective viscosity in this expression and we get this expression as the modified Reynolds number for power law liquids or power law fluids. So by this expression we should be able to calculate what is the Reynolds number of that flow which exhibiting power law behavior. So from this expression we can find what is the Reynolds number. Now the second issue was that what is the critical or the transition Reynolds number, based on which we can understand that this flow is either laminar or turbulent. Now there are several expressions, there are several correlations. In order to find that, one of such is given here. So transition Reynolds number is completely dependent on the consistency, the power law index basically here, not the consistency index. So we see that for a set of power law fluids, set of power law fluids means when n is something, a particular value, then for that set, irrespective of the consistency index, the transition Reynolds number has a particular value or a fixed value. So which means if n is 1 in this expression, n is 1 means it falls back to the Newtonian liquid, the power law behavior reduced to the Newtonian liquid. In that case, this expression results in this number, which again it should be. So similarly, for any value of n, we have a fixed value of transition Reynolds number, based on which we will judge whether the existing flow is turbulent or laminar. So this is the calculation procedure you should typically follow when the calculation of pressure drop is involved through friction factor, because that calculation involves multiple steps. One is that you have to find a suitable expressions for the friction factor. We have to get a chart. If that is available, there is two regimes, one is the laminar and the turbulent regime. So your current operating condition, is it laminar or turbulent? To understand that, you have to find these two Reynolds number. One is the existing current Reynolds number of the slurry that you are handling, and for that category of powered law liquid, what is the transition Reynolds number. Then we can decide whether the flow is laminar or turbulent. Now, for laminar flow, the expression for the friction factor 16 by Re, where Re again is the modified Re modified by the effective viscosity for the power law liquids. And for turbulent flows, as I mentioned, there are several correlations available, and one of such is given here. Once you find this friction factor, you place it in the del P expression, because we knew now that what is the pressure drop and the friction factor expression. So, pressure drop versus this friction factor relation, we know that. So, once we know this one, we can calculate or estimate the appropriate friction factor. We replace that in the pressure drop expression to find out what is the pressure drop in such slurries. So, I hope these steps are clear. It involves multiple steps, but if we follow a due procedure, then it becomes very clear. So, we started with the expression of pressure drop and the friction factor. Then we have seen that how to calculate Reynolds number of that particular slurry, that involved effective viscosity calculation, and this effective, after calculating this effective viscosity, we have found that what is the Reynolds number of that slurry. There are relations available or correlations available to estimate what is the transition Reynolds number or the critical Reynolds number for that category of slurry, or that category of slurry that exhibit particularly power law liquid. Then we calculate the friction factor depending on either the flow is laminar or turbulent. Once the friction factor is known, we go back to the pressure drop versus friction factor relation, and we get the pressure drop value. Apart from this power law, there are other rheological models also available for the non-Newtonian fluids, and one of such set of models are the yield stress models. Now, here in such slurries or such liquids, you need to put a minimum stress in order to initiate the flow or to start the flow. It does not flow as it is. It does not flow if you just put on it on a surface. For example, say the concrete mixture. Until and unless a sufficient angle is provided to the horizontal plane, it does not flow itself. Okay. So, we have to have some initial stress on that, or say the paint coating or inkjet ink and all this stuff, which requires a minimum or a critical thickness to start the flow by gravity. So, the point is that we have to have some initial stress that we have to apply in order to start the flow. So, in these cases, the effective stress versus shear rate can have different profile. Effective shear stress is basically the applied shear stress minus this yield stress. This is the effective stress and the strain rate or the shear rate that is being applied. This behavior either can be linear or it can behave as power law. If it is linear, as in the Newtonian fluids, then this particular model is called the Bingham plastic model. If that is not linear and behaves in power law fluid manner, then that we call the pseudoplastic or the dilatant, like if it follows this kind of behavior like the pseudoplastic or the dilatant fluid, then we have the Herschel-Bulkley model or the yield power law model. So, this particular model is called the Herschel-Bulkley model. So, it is the pseudoplastic with yield stress. When the yield stress is 0, this Herschel-Bulkley basically reduced to shear thinning model. So, we will continue discussing these models, or particularly this Bingham plastic. How do we estimate the pressure drop in such cases? And we will have a look in the other kind of slurry, because this we are talking mostly about the homogeneous slurry. What happens in the heterogeneous slurry? We will continue our discussion on this in the next class. But before I conclude my talk today, let me just again summarize that we started discussion on the power law liquid velocity profile, how to estimate pressure drop in such case, the pressure drop calculations we can directly achieve from the theoretical expression or by the friction factor correlations. To understand what would be the friction factor, we have to understand what is the flow regime. In order to detect the flow regime or to determine the flow regime, we must know what is the Reynolds number of that flow, which we have seen to be dependent on the consistency index and the flow behavior index. And for that set of power law liquid, what is the transition Reynolds number, that we have also seen as in terms of correlations that is provided by the researchers in the literature. From that we can detect whether the flow regime is laminar or turbulent, and depending on that we calculate the friction factor. Once it is known, we go back to the pressure drop expression, replace that friction factor and get the pressure drop. And then we started the discussion on the yield stress model, which we will continue in the next class. Till then, thank you for your attention.